All right, now this is the important slides. I know that there's a lot of information here, but this is all from the Learn Labs. So one of actually the most important distribution that you will need is the normal distribution. It is also known as the Gaussian or the bell curve. And this is kind of the shape of it. I'm sure you all have seen like a bell curve or heard the term like bell curve, maybe when it's like used in terms of, I don't know, grading or testing. That is what's important. And so there are many different kinds of normal distributions. Like normal distributions can come in many different shapes and sizes. This is an example of like, these are actually 4 normal distributions all in one graph. And these are all considered normal distributions because they are all characterized by their mean and standard deviation. Really quickly, I think it's important to know like what are the characteristics of a normal distribution. One, they're symmetrical around their mean. So as you can see here, this is a normal distribution that has this mean, and it is symmetrical about it. The mean, median, and mode of a normal distribution are all equal. So one thing that you can do to test if something is normally distributed, literally see if their mean, median, and mode are the same. Actually, most of the time, just testing the mean being equal to the median is enough, but adding the mode in there, always good to do, to check. The area under each curve is equal to 1 because it is a probability density function. A normal distribution is a probability density function. They're denser in the center, less dense in the tails. That's why you get that like swell in the middle. As I mentioned before, they are defined by the 2 parameters, the mean and the standard deviation. And one more thing about the bell curve that I feel like more mathematically quantifies all of these characteristics is that about 68% of the area of a normal distribution is within 1 standard deviation of the mean. So what that means is you are given this mean and you're given a standard deviation. Those always come with any normal distribution. Let's say in this normal distribution, the standard deviation is equal to 1. And so if we take the mean plus and minus 1, this whole area is about 68% of the entire area under the curve. That makes sense? And similarly, 95% is within 2 standard deviations, and I think it's 99 between 3, 99.7 between 3 standard deviations. And so that sort of like is a more quantitative way to describe like that swell that we see. And so put all these together, the fact that it is centered around its mean and has this like bell curve shape, that is what defines a normal distribution. And normal distributions are everywhere. I think like if you take everyone in the world's height and weight, it follows a normal distribution as well. So real quick, as I mentioned, these are all normal distributions with different means and standard deviations. You can see that these 3, the green, blue, and red one, all have a mean of 0, while the yellow one has a mean of 2. So you can see this yellow one is shifted to the side. With standard deviation basically shows you how like spread out your values are. So in this case, the green one has a standard deviation of 0.4. So that means its values are closer to the mean of 0, compared to something that is also centered at 0 but has a standard deviation of 3. So you can see this is the red line. The red line has a standard deviation of 3. So that means all of their values are much more spread out. And what I mean by that is if the standard deviation is 0.4, 68% of the values are between negative 0.4 and plus 0.4, 1 standard deviation of the mean. Where in the case of the red one, standard deviation of 3, 68% of the values are between negative 3 and positive 3. That makes sense. So that all characterizes their bell curve shapes. So as I mentioned with expected value and variance, the normal distribution has a really nice expected value and variance, where its expected value is just its mean, and its variance is the square of its standard deviation, which is its variance, which is, yeah, its variance. The one thing that is maybe good to know, definitely do not have to memorize this, that the PDF and CDF of the normal distribution is complicated. So as you can see here, we have like 1 over standard deviation multiplied by 2 pi, multiplied by e raised to the power of half, blah, 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 blah. That is the equation that gives you these lines. If you were to plug in like different values of mu is this like kind of like weird mu looking thing, and sigma, which is the typical notation for standard deviation. If you were to plug in different values and plot them on like your graphing calculator or something, you will get these lines. And this is just the formula for the CDF, which is also not very important, but good to know that these formulas are out there. Questions on this?
Yeah, so what happens, so every time the curve changes, right?
Mm-hmm.
Based on the curve, right, you will be able to define that, okay, the center, from the center, right, on the right and the left, it will be 34% each.
Yes.
Then it goes on accordingly, and the last part will be like 0.1%.
Mm-hmm. And like, yeah. So like how far away from the actual middle depends on the standard deviation. Yeah. So in this case, if you want to find like 99% of all the values for the red line, you would have to go between -9 and +9. So the values are spread out much more. Sound good?
Okay.
Cool. Awesome. So we talked about normal distributions, but there is actually the standard normal distribution. And we'll get into it when we talk about z-test next study group. But the standard normal distribution is a very specific normal distribution that has the expected value of 0 and a variance of 1. And why we have the standard normal distribution is so that we can compare different normal distributions and also obtain z-scores. And so what's really cool about standard normal distribution is you can actually take any existing normal distribution, no matter what mean and standard deviation it has, and convert it to a standard normal distribution. Well, I'll talk about the conversion in the next slide. But any questions about like the idea of a standard normal distribution? All right. So we're going to talk about z-score. A z-score tells us how many standard deviations away from the mean a point would be in a standard normal distribution. That definition is just one of many definitions. But these are the kind of important parts. These two formulas on the bottom are what allows you to convert points from this normal distribution to this standard normal distribution. So let's say I have this point over here. If this bar would go away. So let's say I have this point where the red line is. So this red line has is 70. Let's just go with 70. And this distribution, let's say, has a mean of 50 and a standard deviation of maybe about, let's go with about 10. So given that we know the mean and standard deviation of this non-standard normal distribution, we can convert it into the standard normal distribution by using these formulas. And these are also on your Learn Labs. But you would just take each point minus its mu, minus its mean value, and divide it by its standard deviation to convert it to whatever its value would be on a standard normal distribution, which is its z-score. Does anyone need me to repeat that? Yeah, all right. So you can use this formula, x minus mu divided by sigma, to convert any point from here to its equivalent value here. So this point of like 70, you would take 70 minus 50, which is 20, divided it by its standard deviation of 10, and it'll give you 2. Does that make sense? And let's say you had many different kinds of normal distributions, like you had different means and different standard deviations, and you wanted to compare them. You would just convert them to the standard normal distribution, and you can compare them that way. And why and when we would do that, and like examples of that, I'll get into when we get to testing. So once you have a z-score, which is the equivalent value over here, there's what exists is a z-table. There's a z-table, and the z-table, what it does, it tells you the area under the curve up to that point. And what's really cool is the area under the curve up to that point in a standard normal distribution is equivalent to the area under this curve up to this point. And that's why that's helpful. So without using a calculator, or like without doing any intense like area under the curve calculations, let's say I wanted to find the probability of getting test outcomes below 70. What I could do is convert this 70 into the standard normal, which is 2. And then what I would do is I look up this z-table. And z-table is a universal thing. Every z-table is the same. And definition is right here. Table entries represent the area under the bell curve to the left of z. And so earlier we had our z-score here. We had our z-score here being 2. Let me minimize this again. Our z-score was 2. And what we can do here is look up the z-table and look up 2. And so it starts from negative because you can have like points left of 0, but let's look up positive 2. So here we have 2.0 and 2.00, and here we have 0.9772. So basically what that's saying is that the area under the curve here and the area under the curve here is both 0.9772. So the probability of having a score under 70 is about 97. That makes sense? And so because of that, we didn't have to use any complicated formula to calculate the area under this. We just had to convert it to this and then look it up in a table. Questions on that? Let's see. Just to wrap up, yeah, z-scores are associated with the cumulative probabilities retrieved from the z-table. This is the formula for a single point. This is the formula for a sample. Just know that you can actually find the z-score for a collection of items. So let's say we have this distribution and we have like 5 items. We can calculate the z-score for 5 items by plugging it into this formula where n equals to 5. Cool? All right. We'll get more into this like whole sample thing next.
So you can n can equal 5, which is just the number of items
in your sample. Yep.
Like in a sample, but it's not for specific items. It's just for the number of items, correct?
Yep, that's right.
Okay.
Cool. So that is all I have for y'all today. Sorry, I get really flustered when things don't work. So I will get back to y'all on that binomial distribution. Maybe we can do that in like another session. Like I was mentioning at the start that for those of you who weren't here at the start, that I can definitely do an extra session where we're just solving the probability questions from section 11 because they are important for interviews, but not so much for data science. So I'm happy to do an extra session solving all those probability questions. And maybe I can talk about that there. Will be recorded if it happens, but I'll post the message onto Slack and y'all can like react to it or something if you want me to do it. But cool. Any closing questions to section 12?
Just one quick one. Can you go back to the table, Yish?
Oh yeah, of course. Mm-hmm.
So I understand the 2, right? 2.0, but when does it get into being 0.3, 0.4,
Oh,
0.6?
that's a really good question. That's actually a really good point. So z-scores go up to 2 decimal places. So you can have 2.0, you can have 2.05, and if you have 2.05 z-score, you would then look up 2.0 and then go to 2.05, and then you can see like the probabilities actually increase ever so slightly.
Gotcha. Okay.
Yeah, that's a really good point. I forgot to mention that. Thank you.
Is it possible to get into 2. Let's say 95 or?
Yeah, for sure. Yeah, see 2.9 is down here, 2.95 is 0.998. But as you can see, like all these numbers get very, very close to 1. So if you have a z-score of, I'd say if you have a z-score above 3.4, above 3.49, you can safely say that the probability is going to be 1. The cumulative probability is going to be 1. Because in that case, your z would probably be like all the way here on the right, and the cumulative probability, pretty much the entire curve. Cool. Anything else?
When it comes to 1, it's like 100% chances of that event happening.
Yeah. Remember that this is cumulative probability. So, in like this example, what is the probability of getting a test outcome under 100? Because the test scores go from 0 to 100. What is the probability of getting under 100? Would be 1.
Oh.
Anything else? All right. Well, in that case, I will put up this recording when it's done. I will post a Slack message, and please like react to it if you want this like extra session. I can definitely do that. But in that case, have a good night, everybody. Bye.